Hi there, this is Penelope and this is the final video in the series of videos on motion for the Foundation Science program here at WellTech. So we're looking at circular motion in this video. Now we need to get a few words straight. First, a rotation or a revolution means just once round a circle. And we talk about the time taken to go around a circle once as being the period of rotation, and normally we use the symbol T and the time period as a second. For example, if we've got a ball tied to the end of a piece of string and we're whizzing it around at a constant speed in a circle, then let's have a look at the picture. Not very good at drawing, but there's my hand in the middle of the circle. The circle has radius r, and then the speed is this. Whoops, that's the horizontal speed there at right angles. That is the speed of the ball. Now the distance that the ball moves in one rotation is the circle's diameter, and in this case r is the radius and pi is the constant. So you know that the circle has a circumference of 2 pi r. Now the speed is going to be calculated from the distance travelled and the time taken. The velocity of an object travelling in a circular path is in the direction that is at a tangent. That's what I said here. It's in the direction of a tangent to the circle. If the force that's holding the object in a circular path is removed, then the object's going to continue in its current path. And this is Newton's first law. So it may pay to go back and look at that if you don't remember it. Let's have a look here. There's an example. We need to find the speed of an object travelling in a circular path. So we've got clothes in an old-fashioned washing machine, so that means it's in a circle, and they were spun, if you think about it, they were flung when it was spinning to the outsides of the tub. So we've got the period of rotation as being 0.2 seconds, and the radius of the tub, so that's the radius there, is 0.3 of a metre. And we're asked to find how fast the clothes are moving. So the distance is going to be the circumference, which would be 2 pi r. In this case, it's 2 times pi times 0.3, which is approximately 1.88 metres. So they're being spun round that distance. Now the time taken is 0.2 seconds. So the speed of the clothes is going to be the velocity. The v is going to be the distance divided by the time that it takes, the time period. So that's the distance we worked out over here, 1.88 divided by the time that it takes to go around, which is 2 seconds, which will give us 9.4 meters per second if we've approximated to two significant figures. The speed then of a rotating object is found by dividing the distance by the time. And you'll notice there that actually I haven't got the r in there either, because the 2 pi r is the circumference of a circle, so it's the d. Now we can also find the number of rotations made in a second, which is the frequency, and the unit for that is hertz. As an example, we've got here the propeller blades. I won't even try and draw this one. The propeller blades of an aircraft rotate with a frequency of 40 hertz, and the blades have a radius of 85 centimeters. How fast do the tips of the propeller move? Okay, we're given that T is 1 over F, we know that, and we're given F, so it's 1 over 40. And if we use our calculators, that's 0.025 seconds. Now the speed is going to be 2 pi r over t, which will be 2 times pi times, now 85 centimetres equals 0.85 metres. So we're going to put in there 0.85 metres, and we're going to divide it by what we've already found for t as being 0.025. Now get your calculators out and you find that that was 213.628 metres per second, or approximately 210 metres per second to two significant figures. Okay, there's a different sort of question. A racing car's rev counter indicates an engine speed of 4,000 revolutions per minute. Now, that's per minute, and it says 4,000 of them, so it's 4,000 in 60 seconds. Okay, so the frequency is going to be then 4,000 over 60, because there are 60 seconds in a minute. Okay, do that on your calculator and we get that. Thinking about force now and acceleration, when we've got a ball whirling around in a circle as we did before, there are various forces that are acting. There's tension that's pulling the ball inwards, and the direction of the force, as we saw before, is at right angles to the ball's motion. And that force changes the ball's direction, but because the force is always at right angles to the direction of its motion, the speed of the ball doesn't change. Okay, let's have a look at what centripetal force means. The force on the ball provided by the tension in the spring, that is, string, is called the centripetal force. It causes the ball to accelerate by changing the direction, but not its speed. Now, that means then that the ball is constantly accelerating in the direction of the centripetal force. In other words, towards the center of the circle. So we talk about this acceleration as being the centripetal acceleration. So what we've got is again, just the same diagram as before. We've got the ball at the end of a piece of string and somebody's hand in the middle there. Oops, not very good. And you've got tension coming inwards in the string, and the ball is there, and then you've got the instantaneous velocity in that direction. If v is the speed of the ball, then we can work out the acceleration. The acceleration is v squared over r in meters per second squared, or meters per second, and the centripetal force is related to the centripetal acceleration if we're thinking about Newton's second law. So we've got F equals ma, but we've just said that a was equal to v squared over r, so we're going to say that F equals m times v squared over r, and we could rearrange that finally to say mv squared over r. As an example of this, let's look at somebody throwing what we call a hammer. It's not really a hammer, it's just a big kind of stone thing. And the person is throwing it, it's got a mass of 7 kilos, it's swung horizontally 10 meters per second in a circle of a radius 2 meters. Find the force required to keep the ball moving in a circle. Okay, we know the rule. So that the force is equal to mv squared divided by r. Okay, we've got 7 times 10 squared divided by the radius, which is 2. So that equals 350 newtons inwards. We also need to look at centrifugal force, or centrifugal force, and this is the kind of force that you feel you feel it. It's not actually happening to you. When people accelerate, we feel apparent forces. Think of what happens in a lift. When a lift accelerates, a person in the lift feels heavier. Obviously you're not heavier, but a greater force is felt acting downwards, which is in the opposite direction to your acceleration. In the same way, a person moving in a circle experiences a force towards the centre of the... Whoopsie-daisy, no. A person moving in a circle experiences a force towards the outside of a circle. Now, we're looking here at a centrifuge. It's got a wheel that rotates around here, or you can see it in there. It rotates in a horizontal plane. We've got these little things here that are vertical when the wheel's stationary, and when the wheel is spinning, then they turn horizontal. And in the horizontal position, what we usually use these for is separating liquids. So when these are in the horizontal position in here, when they're spinning, the liquids separate with the denser liquids moving further out from the center of the circle. And when the spinning stops, the denser materials are found in the bottom of these separating containers. Often it's easier to measure the period of rotation rather than the speed. So if we've got A equals V squared over R, we can work that out as being 2 pi R over T squared over R, because V equals 2 pi R over T. And if we rearrange that, we get 4 pi squared R over T squared. So the centripetal force can be written like that. See if I can get a red frame. And as an example, we've got a 1 kilogram mass going around a turntable, and it's on there. Friction is holding it in, going around that way. Find the friction that's preventing the mass on it from falling off as it's going round. Okay, friction's providing the centripetal force. The period of rotation is 2 seconds. It tells you that because it's 30 revolutions in 60 seconds. So it goes around once in 2 seconds. The centripetal force is going to be 4 pi squared mr over t squared. Now it's just arithmetic. 4 pi squared times 1.5 times 0.1, because that's in meters now, over t squared. And if you use your calculators, 1.48 newtons inwards, which you could approximate to 1.5